Good morning, sir.
Good morning, madam. Good morning.
Shall we start?
Yes, I'm ready.
Yeah,
Yes, ma'am. A very good morning to everyone. I welcome you all in second session of day 3 of this AICTE ISTE 1 week online refresher program, which is on artificial intelligence and cooperative Noma 5G network. In this session, Dr. Pritam Kumar, Associate Professor from IIT Patna with us as an eminent speaker. I welcome you, sir. It's my pleasure to introduce our speaker. Dr. Pritam Kumar is currently working as an associate professor in the Department of Electrical Engineering, IIT Patna. He did his PhD from IIT Kharagpur in the area of wireless cellular communications. He has around 20 years of teaching, research and industry experience. Physical layer issues in wireless communication, 5G network, error control coding and digital communication system are his areas of research interest. He has published several research papers in various referred IEEE journals, other peer-reviewed journals and conferences. He has already guided 8 PhD scholars in important areas of information and communication technology. He is a regular reviewer of premier journals and TPC member of various conferences. He was the organizing chair of first IEEE symposium on 5G in Asia at IIT Patna in 2016. He has also successfully executed high-value sponsored projects as well as consultancy projects from industry. He is the editor board member of Springer Wireless Personal Communication Journal. He is also mentoring a group of incubates who are working on developing the economical, accessible, and reliable remote medical services for critical patients and outpatients seeking personal health monitoring. He took the lead as PI to establish incubation center in the area of ESDM with focus on medical electronics at IIT Patna with financial support of more than 48 crores from MEITY New Delhi and DIT Bihar government. I welcome you, sir. Now I would like to invite Dr. Pritam Kumar to deliver his talk on enabling technologies for 5G.
Thank you, madam, for my brief introduction. And I'm thankful to Dr. Garima ma'am. He's inviting me, and I'm really happy that Poornima College of Engineering has taken such a lead in sponsoring this very important area of research as an AICTE program. So let me share my slides first. Is it visible, ma'am? Is it visible?
Yes, sir, it's visible.
Okay, thank you.
Kindly put in, sir, full screen mode.
Is it visible? I have put in full screen mode.
Yes, sir, it's visible. Yes.
Yeah.
Yes.
Okay. Good morning, everyone. So let's start this session on enabling technologies for 5G. And these are the outlines of my talk. Introduction, then LTE, 4G, requirements for 5G, challenges and facilitators. And we see that 5G can be achieved in 2 ways. One is evolution and new RAT. RN technology areas, new waveform, millimeter wave, massive MIMO, and I will particularly discussing on NOMA and application of artificial intelligence in NOMA. And finally, conclusion and references, right? So let's start with this very basic slide. Let me take a pointer. Yeah. So if you see this,
sir, slides are not moving. Kindly put in full screen mode.
No. Problem is with this. Now is it clear now?
Yes, sir. Yes.
Yeah.
Yes. Now it's visible.
Microsoft Teams, this is a problem, right? It full screen move, it does not generally move, right? Anyway, so this is a very fundamental slide where we are talking about evolution of wireless cellular communication, and you can see on x-axis we have data rate, y-axis we have mobility and coverage, and you can see a very red linear curve, that is spectral efficiency, and the significance of this is when we are moving from 1G to 4G. we are increasing the spectral efficiency. Spectral efficiency increasing means that that in a given bandwidth, how much data rate you can transmit, that is bits per second per hertz. And because you know that spectrum is a scarce resource, so we have to see that we are able to put more data on a given bandwidth. So two types of switching is there. One is circuit switching and other is packet switching. And invariably, you can observe that the new generations, that is 3.5G onwards, they are using packet switching. So this is basically IP-based network. And coming to this mobility and coverage. So when we are moving from 1G to 4G, this mobility that supporting data rate transmission over high mobile devices and coverage both are going to increase, right? This next slide is visible, slide number 4. So coming to the next slide, so when we are moving from 1G to 4G, what we have witnessed that there is improvement in mobility, coverage, data rate, and quality of service. And we saw that 1G and 2G are circuit switch. 2.5G to 3G, they are working in the both circuit and packet switch mode. But 3.5G to 5G, which is packet switching. And most of the evolving generations are using licensed spectrum, while Wi-Fi, Bluetooth, and WiMAX, they are using unlicensed spectrum, right? Now coming to some brief idea about 2G is you can observe that we have two standards in 2G, GSM and IS-95, and 2.5G, which is mostly for data network, GPRS and Edge. So what you observe that GSM and IS-95 are based for voice communication rate of around 10 kbps. So typical PCM supports 64 kbps, but in wireless communication we cannot transmit at that high data rate. So we are using some encoding technique so that we can transmit our voice communication at 10 kbps. Now coming to this GPRS, that is General Packet Radio Services, and Edge, that is Enhanced Data for GSM Evolution, were proposed to speed with increase in speed in the range of 100 kilobits per second, right? To provide low speed internet, email, etc. to users with mobile devices, right? So this was very important development in wireless cellular communication, that with 2.5G, two standards, GPRS and Edge, we are able to support a data rate of 100 kbps over wireless channel. And this enabled low speed internet and email browsing and all. But it was not sufficient. So these techniques were developed in the 1990s. So what we felt that in the latter part of 1990s that yes, we need more speed. And that led to the development of 3G, right? Now coming to the 3G. CDMA based, CDMA, WCDMA, and other CDMA 2000. Both were popular in different parts of the world, and they supported a data rate of 384 kilobits per second. A quantum increase from 2.5G, which was around 100 kilobits per second. So we are able to increase the data rate by 4 times. But interesting point is 3.5G. That is for enhanced data rate. That is HSDPA, that's high speed downlink packet access. And HSUPA for uplink, that's high speed uplink packet access. They were able to support a data rate of 5 to 30 megabits per second. Now, this is a very, very important development in wireless cellular communication. Why they were important? Because they were able to give similar services to wired technologies like DSL and ADSL. And we can have a data rate of 5 to 30 Mbps. Another important advantage of 5 to 30 Mbps is that the last point is very important. So data rate in excess of 10 megabits per second makes it possible to transmit high data rate multimedia and video content to mobile devices. So minimum data rate we need to have is 10 megabits per second to have this video calling or video conferencing, and that was enabled by 3.5G HSDPA and EVDO. So you can observe that if you're using this 3G mobile phone and having this HSDPA, HSUPA connection, You can go for video calling, video conferencing, everything. Now coming to this 4G. So 4G again has two standards. There is one is the LTE WiMAX, and then we have advanced standard of LTE Advanced. And what you can observe that data rate of 100 to 200 megabits per second, which is a quantum jump over a wireless channel, and WiMAX also supports 100 megabits per second. And the important point is that this 4G based technologies, 4G was based on two revolutionary, I'm using the word revolutionary, new technologies, that is OFDM, orthogonal frequency division multiplexing, and multiple input, multiple output antennas, MIMO. And due to these two technologies, 4G is able to support a data rate of 100 megabits per second over wireless channel. Right. So let us go to the next slide. So just to point out the applications, what are the applications in different generations? So when we move from, when we're talking about 2 to 2.75G, data rate was from 100 to 100 kbps, 10 to 100 kbps. And they were mostly application areas are voice low rate data. But when moved to 3 to 3.5G, and we observed that data rate was a range of 300 kbps to 30 megabits per second. And they were able to support voice, data, video calling, and video conferencing. Video calling, video conferencing is very important application of 3.5G. When moved to 4G, they are able to support a data rate of 100 to 200 megabits per second. And we are able to add, in addition to these services, we are able to add online gaming and high definition TV. This high definition TV was possible only due to 4G data rate supporting of 100 to 200 megabits per second. Why? Because high definition TV streaming application in 4G network typically requires a data rate of 10 megabits per second per stream. So HDTV, there are multiple streams. So definitely we have to go for 4G if you want to have this HDTV services or online gaming. Right. Now coming to this LTE. LTE is a very important term. Generally LTE and 4G, they are used interchangeably. So in November 2004, because from 2000 onwards we have 3G services, but later on we felt that yes, we have to move further from 3G or 3.5G. So we started to work on a technology that is long-term evolution, LTE, and the main aim was to support high performance. This would be backward compatible and wide applications, right? And already we have discussed that promises data rates of 100 megabits per second, and they are optimized for all IP traffic. This is very important. We are talking about IP traffic, right? Moving ahead. So what are the major technologies for 4G? OFDM, right? I will discuss briefly about OFDM for the downlink, and single carrier FDMA, single carrier frequency division multiple access, that is SFDMA for uplink, because OFDM is not suitable for downlink. We'll see that why it is not suitable for, it is suitable for downlink, but not for uplink. So why it is not suitable, and they uses MIMO for enhanced throughput. And when we are moving from 3G to 4G, we are also talking about reduced power consumption. Power consumption should be less. So, and at the same time, we need higher RF power amplifier efficiency. This power amplifier is consuming 70% of the power of any communication system. So we need a RF power amplifier with high efficiency, because this will enable low battery power used by handsets, right? So because we are using portable handsets. Okay. Now some fundamental challenges in wireless communication. So we are moving from 100, we are transmitting at 100 megabits per second, and 5G we are talking about 1 gigabits per second, right? So what are challenges? Why? So wireless challenge is a very hostile environment, right? So these are two important challenges in high-speed wireless communication. One is inter-symbol interference. Other is the frequency selective fading channel, right? Just briefly I will discuss so that you have some feel of what are the challenges in designing 5G, NOMA, and other technologies. So just a simple example where we have a base station which is transmitting to a mobile user. So S of T is a direct line of sight propagation that is being received at a mobile handset. And because your antenna is radiating in all the directions, so there will be multiple reflections, one by a moving vehicle, that is beta STM, ST minus M, then from a high-rise building. So your received signal is not a single path signal. It has multiple paths. I've just taken 2 paths. So Y of T is the output signal, S of T is the input signal that is being transmitted by the base station. And ST minus M is a delayed M time input signal. It is delayed by M time, and N of T is the noise term, right? Just see the bottom diagram where I have shown that the direct path, the bottom one is the signal received by direct path, and other is a delayed signal received by longer path. So because the direct path will be shortest path, and other path, that is reflected path or diffracted path, they will take longer time. So they are received after some delay. And this symbols, so the previous symbol and the current symbol, right, they are interfering with the direct path, right? So this is basically inter-symbol interference, and this causes a lot of errors. And that's why it is a challenging thing in wireless communication. Now, what happens at high data rate? If you're transmitting at 1 Gbps, the last point. If you're transmitting a high data rate, TB decreases the bit period. If you're transmitting at 1 megabits per second, the bit duration is 1 microsecond, right? And if you're transmitting at 1 gigabits per second, the bit duration reduced by further by 1000 times. So what happens that whenever this tau max, this is transmitted signal, this is received signal, and this is the delay, right? So maximum delay when it increases the TB, then ISI occurs. So bit period. So if that reflected signal crosses, if it has more value than TB, so it will go to the next symbol, right? It will go to appear in the next symbol, not in the present symbol. So if it is appearing in the next symbol, so that is not meant for that symbol, and they will interfere, right? So that's why ISI increases when we are transmitting at a higher data rate. So so next challenge is just equalizer. Just equalizer is an important concept. So what we basically do in 3G, particularly in 3G I'm talking about, and we'll see that in 4G we don't require a very complicated equalizer. So if you this is a received signal Y of T, and you take the transfer function of that. So we need a filter at the receiver. Equalizer is a filter at the receiver which has a inverse channel response. So we design a filter with this channel response, and this will try to take care of this inter-symbol interference in 3G networks. But 4G, we will see that what in 4G, what solutions we have in mind. Now coming to the frequency selective channel. So you might have heard about the concept of coherence bandwidth. That is range of the bandwidth over which the channel behaves almost similarly in terms of attenuation and phase. And beyond that, there will be a multiple dip points. So just see that you are transmitting a single carrier signal bandwidth, and we have multipath because wireless channel is invariably multipath. And because the signal bandwidth is more than the coherence bandwidth, what will happen that we'll have multiple dips, deep fades. This is called deep fades, and these deep fades will make your signal this will incur a lot of errors. So if you're transmitting 1000 bits, maybe possible that 500 bits are in deep fade because almost 50% bits will go in the deep fade. And so 500 bits out of 1000 bits are received erroneously, right? They are not correctly decoded. So you have a very high bit error rate of 0.1, right? So so this deep fades. Now how to take care of that? To take care of that, single carrier, that is based, the CDMA is single carrier communication, and CDMA is suboptimal if you transmit at a very high data rate. So yes. So the solution is that you may think that we will increase the transmission power, but that is not the solution. So solution is the multi-carrier system. So we have to go for multi-carrier communication, multi-carrier. Now, rather, we are using single carrier. Why I'm talking about multi-carrier? Because 4G and 5G, they are using multiple carriers. And multiple carriers means that we are not like in CDMA, just we are using single carrier. Now we'll use multiple carriers, right? So what we have observed that till now, what we have observed that in wireless communication, error probability is dominated by probability of being in a fading dip. And this probability is quite high. So there will be multiple errors. So error probability decreases only linearly with increases signal to noise ratio. What I mean to say that if we increase signal power, the error probability only decreases linearly. So we need very high power to take care of this multiple errors. So fighting the effects of fading becomes essential for wireless transceiver design. And single carrier transmission, just now we observed that is not suitable for high data rate transmission of fading channel. So we need multi-carrier communication is an efficient scheme for high data rate transmission. We'll show that how these multi-carrier schemes take care of this intersymbol interference and frequency selective fading, right? This is a very important slide where we are talking about multi-carrier transmission, and what the important multi-carrier transmission scheme is OFDM, orthogonal frequency division multiplexing. So OFDM is basically orthogonal FDM, right? And here what we are doing that this carrier centers, that is we have multiple carriers, and what we observe that the carrier centers, the maximum value of this carrier are put on orthogonal frequencies. So this F1, F2, F3, they all are orthogonal frequencies. Orthogonality, what it means physically is that the peak of each signal, so we have this peak of each signal coincides with trough of other signals. You see that whenever this carrier at F1 has the maximum value, the other signals, other subcarriers, they have zero value. So they are put at the trough. So whenever we sample the signal at this point, we have zero interference from other signals. To do that, the subcarriers should be spaced by 1 by TS, where TS is symbol duration. So this will ensure orthogonality of different subcarriers. Now, when we are moving from FDM is frequency division multiplexing, to OFDM. So this is the frequency bands in FDM where we are transmitting 3 data bits, and there is a guard band. We always put guard band, right, so that they don't interfere. But in OFDM, what we are doing, we are allowing, so in these guard bands, we are also transmitting datas, and we are allowing them to overlap. But due to orthogonality, they will not interfere at the receiver. And at the same time, same band, we are able to transmit more datas, right? So this is basically spectral efficiency. One thing is that we are moving from FDM to OFDM, they become spectrally efficient, right? Another advantage. So what we are doing in OFDM, we are now, so high data rate, right? They are serial communication. We are converting to parallel, low data rate, serial to parallel conversion. In OFDM, we are doing serial to parallel conversion. And if you can observe here that in serially, like we do in CDMA, that is 3G and 3.5G, in 1 second, we are transmitting 4 bits, right? So bit duration is 1 by 4 second. Bit duration is 1 by 4 second. Now by serial to parallel conversions, we are transmitting in parallel these 4 bits, but the bit duration has increased by 4 times. Now, when the bit duration increases by 4 times, all these multipath components will arrive in that bit duration. And this will avoid your intersymbol interference. This is a very important point. Another important point is that in 1 second, we are transmitting 4 bits. So we are not reducing the data rate. We are still transmitting at 4 bits per second. But only advantage is that by serial to parallel conversion in OFDM, we are increasing the bit duration so that all the multipath components are confined to this bit duration, and this will avoid intersymbol interference. So the overview of OFDM, what is OFDM? So orthogonal frequency division multiplexing technique is an efficient waveform to provide high data rate services over frequency selective channel. Already we have discussed. High data stream is split into a set of low rate substreams and modulated on a separate subcarriers which are orthogonal. Better the signal communication over fading channel. Individual subcarriers experiences flat fading. Now it is not frequency selective fading, flat fading, thus allowing simple equalization and high spectral efficiency, simple transmitter implementation because we don't require complex equalizers, low sensitivity timing synchronization, and one type equalization. These are the advantages of OFDM. Now this very important slide where we are talking about the implementation of OFDM using this IFT, that is inverse fast Fourier transform. So what you can observe that to implement this OFDM, we need orthogonal subcarriers. This F1 to F7 just now I have discussed. This need to be orthogonal. So we need to have multiple oscillators, right? And we have to maintain this delta F is equal to 1 by TS, right? So you need a bank of oscillators is required, and very hard to maintain frequency sequence delta because these physical oscillators are, there will be always some deviation from delta F due to this malfunctioning, due to some aging effect, right? So that's why this OFDM was not very popular initially. But what happened that, so this was not very popular. Then what we did, we have implemented this, the orthogonal subcarriers can be implemented using IFT, endpoint IFFT. And when we observe this and we are able to implement this efficient hardware for this IFT, the OFDM technique become very popular, right? And OFDM is de facto standard in 4G and it is very important technique in 5G also. Now, so what are the applications? You may be wondered that why I'm talking about multi-carrier communication and, no, just see the applications of OFDM. This is the baseline technique in 4G LTE, WiMAX, IEEE 802.11 family. That is your wireless LAN, including Wi-Fi, digital audio video broadcasting, extensively studied in 5G and beyond, new radio, narrowband IoT, UWA, radar, VLC, including NOMA. What are the challenges? What are the challenges in OFDM or multi-carrier communication? They are highly sensitive to carrier frequency offset, that interference compensation is required, and they are also subjected to high peak to average power ratio, PAPR, because we have multiple subcarriers. So they may add up constructively, and so that the peak power will be more than the average power. So this will drive your power amplifier at the receiver in the nonlinear region, and this will introduce distortion, right? So to avoid that in the uplink, that's why I have told you that uplink where PAPR will be very critical. We are not using OFDM, we are using SCFD. We are going again for SCFD. SCFDM is nothing but it is a DFT precoded OFDM. It is again a multi-carrier communication, but in this case, we are doing this DFT precoding so that eventually we transmit as a single carrier transmission. Now, CDMA has a lot of advantages, right? And that is the reason that we thought of combining the advantage of CDMA with OFDM. OFDM has its own advantage, CDMA has its own advantage. So let us combine these two. So what we are doing in that is the technique called multi-carrier CDMA, right? MC-CDMA. So if you observe here that we have this serial data transmission. So each bit is first being spreaded. We are doing the spreading. And we are doing this spreading by pseudo PN code, PN sequences, which has N chips. And what we are doing is that we are transmitting now each chip on orthogonal subcarrier. We are transmitting this each chip on orthogonal subcarrier. Sorry. So what we are doing, we are doing spreading. The spreading length is equal to the orthogonal subcarriers, and the typically Walsh code, handmade code, or gold codes are used, and each chip with different orthogonal subcarriers. We are modulating each chip with the different orthogonal subcarriers. Now, another concept is that there are some issues in MC-CDMA also, or OFDM also. To take care of that, we are basically doing this two level of spreading. One is by the spreading code and other is by the complex spreading code. Here what we are doing, just see that what we are doing, we have orthogonal subcarriers as usual in OFDM, And then what we are doing, we are multiplying this again by complex orthogonal CI codes, and they are basically orthogonal phase shift to different subcarriers. We are adding one more level of orthogonality by just adding orthogonal phase shift, right? And this is basically called orthogonal multicard transmission using complex carrier interferometry code. Interferometry is a very important concept in physics, right? Where we observe that we have distinct peaks and nulls if you transmit multiple carriers. So we are using the same concept here. This is called CIMC CDMA, right? This is a very important concept. And just now I have told you that they are using what we are doing here in CIMC CDMA that was proposed in 2004, seminal paper by Natarajan. We are using unique orthogonal phase shifts to different. So we are doing what we are doing. We are just adding one more phase shift, unique orthogonal phase shift to different subcarriers. Enhance performance in terms of BER and PAPR, because BER and PAPR is a big issue, and flexibility related to other conventional spreading codes. The length n can be of any integer. In this, what happens if you are using Walsh-Hadamard code? They are limited by the orthogonal number of orthogonal codes, right? But in the case of if you are using carrier interferometry codes, their length can be of any integer value, right? Can be of any integer. And just you can observe that 2 pi by n, then 1 2 pi by n, and 2 2 pi by n. These are the orthogonal phase shift. 2 pi by n is basically orthogonal phase shift we are doing, adding to the each subcarrier in addition to the orthogonal frequency. Now, let's discuss few important research areas in multi-carrier communication, because that will drive us to the 5G and beyond 5G. So these are the important research areas in multi-carrier communication. So one important area is that how we can accommodate more users than the orthogonal dimension, because we know that in multi-carrier communication they are limited by number of orthogonal subcarriers. So we can only support a fixed number of users there. That is the hard limit. Now in NOMA, so what we have to think of that, how, because in 5G the number of users that is being added is exponential. The data rate is increasing exponentially, right? It is increasing, at a very rapid rate. So to accommodate more users or to accommodate more data rate, what we need to have is that the concept called channel overloading, that was used in 3G and 4G, and other concept is NOMA, that is used in 5G. Second important research area is that seamless coverage to urban, semi-urban and remote areas, because there are so many areas which are not covered by this terrestrial network, right? So, or they have weak connection in suburban areas. So for that, the solution is multi-carrier satellite communication. Satellite communication is also important, very important for 5G. And then last point is that multi-carrier communication with high data rate, just now we have observed, with high data rate over higher frequency bands, leads to significant interference due to carrier frequency offsets. Whenever we are going for high data rate and over high frequency band, and you have these mobile devices, right? If you have mobile devices, so they will, if you are moving, you will always have a Doppler spread. If you are moving, you will always have a Doppler spread, and that Doppler spread will be quite significant if you are moving in the higher frequency band in terms of gigahertz. So there will be a lot of interference. And to take care of that, you need to have a improved multi-carrier waveform in 5G, and one of that can be discrete fraction Fourier transform based DRFT based OFDM, because what we observed that we are using IIFT, which is suboptimal in case you have very high carrier frequency offset. So we have to design a waveform which is optimal in case of high speed over higher frequency band transmission, right? So we have designed new waveforms. Now NOMA, when you talk about NOMA, NOMA is basically extending the channel capacity, right? Extending the channel capacity. So what is important? That's called, first we'll discuss about channel overloading. So efficient use of the available radio spectrum is a major requirement for future wireless systems. So we want to add more number of users in a given bandwidth. OMA techniques, there are two techniques. One is NOMA, one is the NOMA and other is the OMA, right? So OMA techniques like orthogonal CDMA, TDMA, FDMA, right? they are subjected to they are not subjected to any interference up to n users. N is the orthogonal dimension, but have a hard capacity limit, right? That is, number of users can be only n, where n is the orthogonal dimension. When you're talking about OFDMA, the orthogonal dimension is the number of orthogonal subcarriers. We talk about orthogonal CDMA, orthogonal dimension is the number of orthogonal spreading codes. When we talk about TDMA, that is the number of orthogonal time slots. So only that much user you can support. Now to tackle so many users in 5G, you have to think of some innovative idea. So in multi-user communication, channel overloading refers to accommodate more number of users, active users, than that can be achieved with orthogonal dimension. And NOMA, there's non-orthogonal multiple access in 5G supports a higher number of users than the number of orthogonal resource slots with the aid of non-orthogonal resource allocation. This is what we are doing in 5G, right? The challenge is what? High level of interference due to additional users. Whatever additional users we are adding, they will have high interference level. So just have a look of this on diagram. Diagram, I am able to show the concept of channel overloading. So here what we are doing is these blue colored mobiles, they are basically the users which can be accommodated with orthogonal dimension. And this yellow colors are the users which are not accommodated because they have the hard capacity limit. So we have to devise some technique where we can accommodate these users also. So what we do in multi-carrier transmission or MCCDMA, we are designing some innovative codes, right? So that we can support these extra users, but there will be interference. There will be high level of interference. Now, how to remove this interference? In NOMA also, we are using SIC, successive interference cancellation, right? So, but that too you have to do in multiple stages. So this is called two-stage. Just I have shown you two-stage interference cancellation receivers. So you can see that this receive signal at the user terminal, the receive signal at the user terminal, they will be combination of both the set 1 users and set 2 users. Set 1 means that they are orthogonal users and set 2 are non-orthogonal users, right? They will be received, and what we'll do, we'll if the set 1 match filters, we'll try to estimate the interference from the set 2 users, and this interference is being removed from the set 2 users, right? So signal detection is carried out iteratively. Each iteration consists of 2 separate stages. This way we are doing the interference cancellation in NOMA. Now, just I will discuss one scheme where we can have more users than the orthogonal dimension. That we are doing in channel overloading or NOMA. So what we are doing, this first n users, we are giving this Walsh handmade codes which are orthogonal. Fine. We are doing I50 with CI. And the additional users, we are using same Walsh handmade code, but here we are using POCI code. This is pseudo orthogonal. They are not exactly orthogonal, they're pseudo orthogonal. And in this way, we are able to add more users and they are transmitted, right? But there will be interference. What we did, we tried to find out that suppose we are adding 16 additional users, right? 64 is the orthogonal users and 16 extra users. In that case, if you observe that the first plot, that is simply a scrambled Walsh handmade spread where we are using scrambling codes that basically we are doing in 3G. So in that case, you see the performance is very poor due to high level of interference. But when we used this W spread CI, where orthogonality, the property of diversity property of Walsh handmade code and the diversity property of CI codes are used, the performance is quite impressive. And it's not very close to single user bound without interference, but we are able to support 16 extra users, and we are able to get a bit error rate of order of 7 into 10 to minus 4, right? So this is a very important advantage of going from MCCDMA to CIMC CDMA. No, finally, this is the concluding slide on OFDM. So what we are doing in OFDM, this is the foundation for LTE, that is 4G and Wi-Fi, and this is going to be important for 6G also, 5G also, and 6G also. So just see that what we are doing in OFDM. This is a complete diagram, whatever we have discussed. So we have data. We are doing this coding and modulation as usual, whatever modulation technique we are using in coding. Then we go for serial to parallel conversions. Then we are doing IFT, which is foundation of OFDM system. Just see this extension of this diagram block. So what we are doing, so data transmitted via closely spaced narrowband subcarriers. IFT operation ensures subcarriers do not interfere with each other. So this is the diagram where we show that the subcarriers are overlapping, but they are not interfering because IFT operates orthogonality of the each subcarrier. In addition to that, we are adding cyclic prefix. So this helps maintain orthogonality despite multipath fade. So there will be interblock interference in OFDM, right? Because we are transmitting parallel streams. So there will be interblock interference, and just we are trying to append some part of the present block. What we are doing in cyclic prefix, that same block we are adding some extra bits in the beginning, right? The cyclic prefix, and then finally we are doing this windowing and filtering, right? Windowing reduces out of band emissions. So windowing is important concept, and then we are doing this filtering operations, right? Now, coming to this 5G, right? So just till up to this point, we have discussed basically on important technologies for 4G and the limitations of 4G in terms of number of users it can support. See, high data rate you can do by using this OFDM and MCCDMA, but the other challenge is that how many users you can support with this high data rate. That is another challenge. For that, we have this channel overloading and NOMA. Now, so that's why NOMA is very important for 5G, but there are other challenges in 5G, right? So just we'll see that what are the challenges in 5G. So when we talk about 5G, so we are talking about data rate in 1 to 10 Gbps data rate in real network. We are talking about 1 millisecond round trip latency. Latency should be 1 millisecond. It is very stringent requirement. High bandwidth in unit area, enormous number of connected devices, almost 100 times coverage. This is also advantages in 5G. Almost 100 times coverage for any time, anywhere connectivity. Reduction in energy used by almost 90%. Now at the same time, when we are adding enormous number of devices, we are increasing data rate from 1 up to 1 to 10 Gbps. At the same time, we are talking about reduction in energy used by almost 90%. And then we are talking about low power consumption, right? So this right side diagram will tell you briefly about that. So when we talk about capacity, so in 5G, we are supposed to cater 10,000 times more traffic, 10,000 times more traffic compared to 4G. 10,000 times is, expecting that we are going to implement 4G, 5G in maybe around 2023 to 2025 time span. So, and devices are going to increase from 10 to 100 more times more compared to this, all compared to 4G. Latency, we are talking about 1 millisecond. Battery life, we are talking about 10 years for IoT nodes, right? And 10 gigabits data rate for peak data rate, user data rate, and the low end data rate should be 100 megabits per second and ultra reliability. These are all of the requirements of 5G. And if you can see the physical limit, we are very close to the physical limit, right? So we are very close to physical limit in 5G. So these are the basic challenges of 5G. So just I will discuss one of the challenge. From there, you'll understand that how 5G implementation is very challenging, and we are still struggling, right, to meet the requirements of 5G. So if you talk about LTE, that is 4G, because we are talking about latency of 10, moving from 10 millisecond to 1 millisecond latency. If you talk about 5G, 4G, we have 10, the latency in 4G network is 10 millisecond, right? Where 4 millisecond goes in the processing in the mobile handset, 4 millisecond in the base station, and in the core network, internet, another 1 to 2 millisecond and 5 to 10 millisecond respectively. So this is case of 4G. When you move to 5G, where we're talking about 1 millisecond latency, just see what need to be done. All the processing in mobile devices should be done in less than 0.5 millisecond, and everything at the base station side should be done in less than 0.5 millisecond. Right? For that, we need very high-speed processor, a lot of advancement in DSP, a lot of advancement in VLSI technology, right? Then only we'll be able to realize the speed of one delay, end-to-end delay of 1 millisecond, right? Till now, we are not achieved. We are around 4 to 5 millisecond. Now coming to this application area, right, where we are talking about the application area that is in 2020 and beyond, what is all about wireless technologies. So wireless beyond 2020 outlook, right? So if you see that there are two basically service areas, application areas. One is the enhanced mobile broadband, EMBB. So whatever mobile we are using right now in 4G, there will be enhancement in that. Enhancement in which aspect? Very high data rate. We are talking about 1 Gbps, high spectrum efficiency, 10 times more spectrum efficiency, high mobility. So in 4G, the target speed was 200 km per hour, but when it comes to 5G, it is 300 km per hour. And low PAPR in the uplink, because peak to available power ratio is biggest challenge in one of the important challenge in 4G. Simplified receiver design, because we are aiming for low power consumption. We are aiming for low power consumption. So low power consumption means that your receiver design should be very simple, right? Otherwise, it will eat up your battery life. And then high densities. So the mobile users are, the number of you. Now, if you see that everyone is carrying more than one wireless device, handset, laptop, PDA, right? More than one mobile handset, right? So, and number of users are also increasing. So density will be quite high. So how to support this high density mobile broadband users, right? It's not so easy, right? It's not so easy. Now coming to other type, which is very typical of 5G. Here we are giving more emphasis on, in addition to this enhanced mobile broadband, we are giving emphasis to massive machine type communication. That is not predominant in 4G, but in 5G it's very predominant. That is massive machine type communication. What is that? One area is for machine type communication is IoT, right? So what are the requirements? We are removing non-orthogonality, because till now what we have in discussed about orthogonal transmission, right? We are talking about orthogonal transmission like OFDM, MCCDMA and all. But now we are talking about non-orthogonal, and here comes NOMA. NOMA is not orthogonal transmission, non-orthogonal multiple access, NOMA. But the requirement, because the number of IoT devices are in millions, so we need high spectral efficiency to support so many devices. Low complexity is very important. Low PAPR is important, and now the transmission will be asynchronous, right? When you talk about device-to-device communication, machine-to-machine communication, they are invariably asynchronous. Minimum out-of-band radiation, because the number of devices that is being connected is too much. So we want that out-of-band emission is very important. So filtering technique or windowing technique is very important. So what are the example of this in IoT networks? That is sensor networks for smart grid, smart cities, smart homes. So we have smart grid, smart cities and smart homes. They are important applications of IoT. And at the same time, we have intelligent transport systems. That is ITS. Now, the third category is it is exclusive. See, this IoT was there in 4G also, but third category, that is ultra reliable and low latency, that can be only met if we are going from 5G, where we are talking about reliability of 99.99%. We are talking about the latency of around 1 millisecond. So why these requirements? Now, question comes, why these requirements? Because there are some applications where really we need ultra reliable and low latency communication. What are those? So what do we want? Sorry. So what basically is requirement in ultra reliable low latency applications? The latency should be some millisecond, right? Immune to Doppler, right? At the same time, we want that this to Doppler, because this applications, they may be mobile application, right? Low complexity is always a requirement, because then only it will take care of your reduction power consumption. What are the application? Tactile radio, autonomous self-driving vehicles. Just for example, I'm talking about this self-driving vehicles, that is autonomous. Now you can imagine that this autonomous self-driving vehicles, if it does not have, latency in milliseconds, because you have to take a decision in milliseconds. At the same time, whatever communications you are using, that should be ultra reliable. Otherwise, it will be chaos, right? This self-driving cars will have, major disasters. So it should have this cognition capacity or thinking capacity or intelligence when we have a car with a driver. But that intelligence can be only possible if you have a communication link which can ensure you delay in the range of 1 millisecond. It should be reliability should be 99.9%. Then only it will be a successful implementation, right? So this is again a major requirements on 5G or application layer of 5G. Now let's discuss something very quantitative way, right? Till now we have discussed qualitative way. Now let's discuss quantitative way. What are the requirements of on something around 2020? This, when we talk about beyond 2020, we are not restricted only on 5G, right? Beyond 5G also, maybe probably 6G, right? So what is the important point to observe is that data rate increases 10 times every 5 years. This is very interesting. Every 5-year data rate will increase 10 times. Already we have seen when we move from 1G to 2G to 4G to 5G, data rate is increasing every 5 times. It is increasing 10 times. Now expected data rate after 10 years, maybe around 2030. 1 terabits per second for Wi-Fi, 100 gigabits per second for cellular communication. How to tackle? How will tackle this high data rate? This is one question. Now coming to this enhanced mobile broadband. The data rate will be more than 10 gigabits per second, peak data rate. 100 megabits per second if you are moving at high mobility, because in high mobility you can support 1 gigabits per second. If it's point-to-point fixed type of communication, we can go for 10 gigabits per second. But when the user is moving with 300 km per hour or 500 km per hour, like in aeroplanes and bullet cars, bullet trains, the target rate is 100 megabits per second and 10,000 times more traffic. This may be, so enhanced mobile broadband has to take care of these requirements. Machine type communication, that already we have discussed just now. And then we are talking about ultra reliable machine and low latency type communication, where we are talking about reliability of 99.99% and latency of less than 1 millisecond, right? And if you see this diagram, it clearly shows that these 3 type of requirements, whether enhanced mobile broadband, machine type communication, that is IoT, and this ultra reliable low latency complexity, they have different requirements, right? And I have shown with the different colors. So when talk about enhanced mobile broadband, so here we are more stringent, we are more confined to area traffic capacity, peak data rate, user experience data rate, and spectrum efficiency, right? As well as mobility. So this last dotted line is the physical limit. We are about to touch the physical limit in terms of mobility, in terms of spectral efficiency, in terms of user data experience, peak data rate, area traffic, networks. But when it comes to your IoT application, that is machine type communication, that is blue colored, right? So here, these are not these requirements of area traffic data, peak data rate, right? They are not so stringent, right? So they are at a lower level, right? But when it comes to machine type communication, sorry, ultra level low latency communication, you can just see that connection density or latency, they all are at the physical limit, right? Because we want a very reliable and low latency communication. Moving further, just about one slide on tactile internet, right? Revolution in communication, tactile internet. Just I give you an idea of tactile internet because in 4G, right? 4G, we are talking about content communication. So up to 4G, what we are interested, communication is to deliver content, that is video, voice, video, SMS, right? That we want. But in 5G, we have steering and control communication, right? Why we are controlling steering and control communication? Because these services, healthcare, traffic, sports, education, manufacturing, and all this, grams, etc. They need this. They need to be, available within a click, right? It's not a simple content, individual content, voice, video, SMS. So what we are doing to steer and control virtual and real objects in 5G introduces various challenges. That is augmented reality and virtual reality. Just basically we are talking about augmented reality and virtual reality, where these services should be available in a whole as content, right? Content will be these services. Content will be these services itself, not voice, video, and this. Right, so everything should be available in terms of augmented and virtual reality. Well, now how to move from 4G to 5G? How to move from 4G to 5G? Let us see how we have moved. So 5G will be achieved, is being achieved. I cannot say it will be achieved, is being achieved in two paths. One is the evolution path and other is the revolution path. That is a new RAT. So what we are telling is that evolution of LTE Advanced will continue beyond in a backward compatible manner with the goal of improving system performance in the bands below 6 GHz. So what we are doing, we are trying to evolve 4G network or 4G advanced network so that it can support services up to 6 GHz, because 4G is basically around 2.4 GHz, right? Now from 2.4 GHz, we are moving to 6 GHz because 6 GHz will offer you more bandwidth. So you can add more users and you can transmit a high data rate. So we are trying to enhance this 4G. What it means that it is also expected that at least a part of 5G requirements can be met by the continued evolution of LTE Advanced. Right? This is what we are doing right now. We are trying to advance this 4G network so that a part of 5G requirements will be met by that in the 6 GHz band. Right? We are talking about 6 GHz band. Now the second track is commonly known as the new RAT, new radio access technology, where NOMA will come into picture. The second track is commonly known as new radio track in 3GPP, which is not limited by backward compatibility. So the new technologies, the revolutionary technologies we are talking about in 5G, they need not to be backward compatible and can integrate breakthrough technologies to achieve the best possible performance, right? So this is two paths. One is to summarize two paths, one evolution path. So the 4G advanced network will be evolved to 5G to meet some of the requirements of 5G in sub 6 GHz band, and other will be totally a disruptive technology, revolutionary technology, which will take its own path, new path. So ITU, that International Telecommunication Union, has finalized work on the vision for 5G systems which includes support for explosive growth. So what 5G will be meant for? It is support for explosive growth of data traffic, support for massive number of machines type communication. So one is that explosive growth of data traffic because the number of mobile users that is being added is exponential. Support for massive number of machine type communication because machine type communication, you know that is predominant now, and support for mission critical and ultra reliable and low latency communications. There are three visions for 5G. One is that support explosive growth of data traffic because we all know that we all are using mobile devices extensively, so that data traffic will be explosive. Massive type communication, number of devices that is being in the IoT network is tremendous. And third is that mission critical and ultra reliable low latency communication, that is your drone communication, or it is maybe tactile internet, it may be due to augmented reality, everything will come under this mission critical and ultra reliable low latency communication. So 4G LTE advanced networks are mostly deployed in legacy cellular bands from 6 MHz to 3.5 GHz. So already I have discussed that 4G LTE advanced, whatever we are talking about in 4G till now, they are mostly developed in 6 MHz to 3.5 GHz. But what we have to do, we have to evolve this, that evolution path. This technology will be evolved to support services up to 6 GHz, right? 6 GHz is a quite high frequency band, and we have enhanced our 4G network so that it can exploit the bandwidth at 6 GHz. Now talking about key technologies, let us discuss about key technologies or enabling technologies. So let us see what are the technologies which are important. So evolution from LTE advanced, right? This is the first section on that. One is the software defined networking, SDN. You might have heard about SDN. Why this SDN is important in 5G? So it utilizes the resource efficiently using software defined networking to serve a large number of devices. When we have large number of devices, for each device, when the number of devices are increasing, you cannot change the hardware, right? So you have to define it functionality in the software. So if the number of devices is doubled, one way is that replace the hardware to support so many users. Other way is that can we reconfigure that radio such that it can support more users. Second, we talked about MIMO in 4G. Now we are talking about full dimensional MIMO in 5G because now we have bandwidth in excess of 3.5 GHz, right? We are talking about 6 GHz, so we have more bandwidth now. Utilizes a large number of antenna placed in 2 dimensions to form narrow beams in both the horizontal and vertical. So full dimension MIMO is that it generally in 4G what we are doing, we are forming the beams in only one direction, either horizontal or vertical. But now we are talking about 2D antennas, 2 dimension antennas, which form narrow beams in both the horizontal and vertical directions. Improve the system performance by utilizing high order multiplexing, multi-user multiplexing. The more users, more multi-user multiplexing. And third point is that significantly improves beam forming and spatial multiplexing. This is very important. Last point is very important because now we have beam forming in 2 directions. So it will improve the beam forming because we have 2D MIMO and we will have spatial user multiplexing capability. So now we can add more users both in the horizontal and vertical directions to have this multiplexing gain. This is all about full dimensional MIMO. Now other is license assisted access LAA using LTE, right? So this, what is that? LAA, what is LAA? The use of unlicensed spectrum. There are a lot of unlicensed spectrum, right? So the use of unlicensed spectrum is now being considered as a potential complement to LTE systems operating in licensed spectrum. So we have to complement this licensed spectrum with the unlicensed spectrum. Moreover, first using the underutilized resources in LTE is an active research, and LAA is expected to improve the utilization efficiency of unlicensed spectrum and licensed spectrum both. So this technique is basically how to optimize the use of licensed as well as the unlicensed spectrum, because spectrum efficiency already we have discussed in the beginning. Spectrum efficiency is very important to support more users and more data rates. Now, the second part. This is all talking about. I am talking about evolution path. I'm not just now. I have not come to the evolution path. Evolution path. Another important technique is NOMA. Why? Because we understood that when we are in the IoT regime, or when we are talking about ultra level low latency communication, the number of users or the reliability is very important, right? The reliability and delay is very important. Now, if you go for OFDM, just what we use in 4G, the number of users are restricted. So why we are talking about NOMA? Because NOMA increases capacity, number of users, by multiplexing users to same resource. So resource is fixed. Same resource at the transmitter, we are adding more users in the same resource, what we have used in OMA, but there will be interference, and separating them with successive interference cancel at the receiver. This is the concept of NOMA. I will discuss more on NOMA in later slides. At the same time, we are talking about green communication because low power consumption is very important and less carbon footprint to the nature. This is very important, right? Because we cannot add on devices, a lot of IoT devices, and we cannot afford to have more carbon footprint. So carbon footprint should be less. So the power consumption should be less and the carbon footprint should be less. That comes in the green communication. Then carrier aggregation enhancement, CAE is also important. Machine type communication, then wireless security, because wireless 5G, we are doing a lot of things wirelessly, everything is wirelessly. So wireless security will be an important area of evolution. Now, coming to this revolution path, right? Revolution we are talking about. So the term what is used in the new RAT in 5G system or NR. Generally, they use new radio. But the term this revolution path is new radio. Should meet all 5G requirements. The aim is that 5G new radio should meet all 5G requirements, as it would eventually need to replace the previous generation system in the future. The aim is that all the requirements 5G should be met and it should replace the previous generation in the future, right? Like gradually this 2G is becoming obsolete because we have 4G, 3G is still prevalent. But when this new revolution will come, it will replace all the previous generation of that is 3G and 4G. So we have new technology, that's new radio. So the new RAT track, the second track, is also expected to have a scalable design that can seamlessly support both above and below 6 GHz bands. So one thing is that because we have developed a lot in 5G around, we have developed technologies for 5G around 6 GHz also, right? And now we are talking about new radio, which will be operating at much higher frequency band in millimeter wave band, right? More than 28 GHz. When we talk about millimeter wave band, typically we are talking about frequency band more than 28 GHz. So one hand we have 6 GHz, other hand we have 28 GHz and more and above. So we have to see that they are expected to have a scalable design that can seamlessly support both above and below 6 GHz. So what we need new waveforms and multiple access radio technology. What requirement is that? A new radio is that new waveforms, because the present waveform will not support this new radio, and we should have a multiple access radio technologies. And other important area is that efficient designs for massive MIMO and millimeter wave. So new waveform is one area, or multiple access is one area that need to be developed for new radio. Other is efficient design for massive MIMO. So from MIMO, we have moved to two-dimensional MIMO that we discussed in evolution path. Now we are talking about massive MIMO. Here the number of antennas is more than 100, right? Number of antennas is more than 100, and it has its own advantage. And then we are talking about millimeter wave, that is the frequency band more than 20 GHz. So just see this spectrum. So we have 6 GHz. So this is where we are trying to develop 4G and 5G evolution path. Then we are talking about 5G, which will predominantly, right now we are concentrating on 24 GHz to 100 GHz.
And the advantage that this basically is millimeter wave, large millimeter wave bandwidth opportunity. The requirement why we are moving to 24 gigahertz to 100 gigahertz, because this will have enormous bandwidth. So we can have more devices, because number of devices is going to increase. Already we have seen in Outlook 2020 that number of devices will be quite high. Data rate will be in terms of 10 Gbps and more, right? And if you're talking about Wi-Fi, we are talking about 1 terabits per second. So such a high data rate in Wi-Fi or in a cellular network of 10 Gbps, right? They need a very high frequency band, more bandwidth, right? So here, that's why we are talking about 6 gigahertz is going to be matured, is almost matured, is almost occupied. But now we are talking about bands in 5G, that is new radio, more than 24 gigahertz to 100 gigahertz, right? So what we need, key technology, innovative technologies, improved waveforms need to be there to support this high frequency band. Massive MIMO, because I have few slides on that. Massive MIMO is required to exploit such a high bandwidth. Millimeter wave, just now we have discussed. Head nets and small cells. Now what will happen that when you move to very high frequency band, the propagation, there will be a lot of path loss. And this high frequency band cannot penetrate any obstacle, right? They are blocked by the obstacles because the lambda is very small. So path loss is high. It is hindered by the blockage. Third is that this atmospheric attenuation or absorption, you can say, by this air droplets or by these gases is quite high, up to 10 dB per kilometer, up to 10 dB per kilometer. So we have to go for small cells because this high frequency band cannot travel longer distance. So we are talking about small cells and we are talking about heterogeneous networks. When you come to small cells, so your network will be heterogeneous, right? Where we have macro cells, we have micro cells, we have pico cells, we have femto cells. So this network will be heterogeneous. And this is very good for device-to-device communication because generally device-to-device communication is for short distance, right? And then we are talking about cloud RAN, right? Everything radio access network will be on cloud. Till now, what we are talking about cell-free network, right? There will be no cell, right? So everything will be in the cloud. So radio access network on cloud, right? That's basically your cloud RAN. This will part of your revolution path of 5G. Now come to this millimeter wave. Just one or two slides of millimeter wave because that is very important for 5G. This technology for 5G. So higher frequency antennas elements are smaller. So if you are going for higher frequency, antenna elements are smaller. Huge amount of spectrum available in millimeter wave band. Improved performance in dense crowd because dense crowd means that you have more number of users and you have to beam it to individual users. So narrow beam is one advantage in millimeter wave, that your beam will be very narrow and you are using so many antennas, so you can steer the beam. Student candidate for higher per link data rate because you have enormous bandwidth. So and you can beam it to a particular user. Even in dense crowd, so dense crowd means what? A lot of users, like in stadium, right? If you are in a stadium, there are lakhs of spectators, right? They are very closely spaced. They all are using this mobile handset. They all are using your wireless devices. Coming to dense crowd area, right? Urban areas, there are so many areas which are densely populated. Now, to serve those users, and those number of users are increasing. The data requirement is increasing. How to support? Right? So we have to use this higher per link data rate, and this millimeter wave can do that. But there are challenges. Nothing comes free. There are challenges. So we need multiple antenna arrays are required for spherical coverage because the beam width is very small. So we need multiple antenna arrays for spherical coverage. IC and system design. Now integrated circuits and system design is very embedded systems, everything. So there will be increased complexity because now what we have done till date, we have designed circuits which can operate up to 6 gigahertz. Now we are talking about millimeter. The lambda is very small, right? So we have designed IC technology in that area. The system design should be for this lambda in terms of millimeter wave. So the complexity is going to increase. And discovery and tracking of mobile devices is very difficult in millimeter wave because it has a very short, you can say, propagation length, right? It can, because due to very high atmospheric attenuation and blockage, it cannot travel to a longer distance. So tracking will be difficult in the case of mobile devices. There are a few challenges in, you can say, millimeter wave, but there are solutions also, right? So now another important technique in 5G new radio is massive MIMO. Just you can see that we have antennas in all directions, right? Horizontal, vertical, and space, right? Everywhere we are putting more than 100 antennas, or you can say. So now these antennas can be your beamform. We are doing a lot of beamforming where you can see that we have multiple users, and all these users are being supported by a single beam, right? This is the beauty. And so they can be supported with a single beam. So you can add more users here, right? You can transmit at higher data rate also because you have multiple antenna. It has a special multiplexing gain, right? So a special multiplexing gain will increase your data rate. And this high number of antennas, it can support a beam forming such that it can just be confined to a particular user. So what is the advantage? Multiple antennas at transmitter and receiver provide multiple signal paths and hence better performance in terms of data rate and link reliability. Reduced transmit power, fast fading prevented, power efficiency, right? How it is achieved? It is achieved through spatial multiplexing because your antennas are placed in space. So you have that gain. Spatial diversity because you can have more and receive antennas. We have array gain because we have multiple arrays here, and we have multi-user diversity. But there are multiple users, so we will get the multiple user diversity gain, right? Now, best part is that, no, one more slide on massive MIMO. So massive MIMO, when you talk about, so capability to improve. What is the advantage of massive MIMO? We have more than 100 antennas. So it can improve the radiated energy efficiency by 100 times, and at the same time increases the overall capacity by 10 times. Massive MIMO systems can put together with the help of low power and less costly components. Massive MIMO makes the multiple access layers simpler. We'll see that how it is making simple multiple access layer. And massive MIMO increases the strength equally against unintended man-man interference and internet jamming because it can beam your signal in a very narrow area. No, this is an important slide. Best part is that massive MIMO at millimeter wave. That's why another important area of research is millimeter wave massive MIMO. Millimeter wave massive MIMO. So this massive MIMO at millimeter wave. Why massive MIMO at millimeter waves? Massive MIMO resolves millimeter wave issues. The best part is that millimeter wave has so many issues, and massive MIMO can resolve that. How? Let us see. So just this is a typical diagram where I'm trying to show that the value of lambdas, right? So when you talk about this 28 gigahertz to 28 gigahertz one window, then we have 38 gigahertz, 60 gigahertz, 17 gigahertz, 90. There are different windows in millimeter wave band, right? So 100 gigahertz spectrum in millimeter wave band, we are talking about something from. So what's happening that if you're transmitting at these bands, and you see this bottom diagram, so high path loss due to antenna aperture size and atmospheric attenuation. Your antenna size is very small, and when you are going from millimeter wave, the antenna size is very small. So high path loss due to antenna aperture size and atmospheric observation. So if you see this diagram, frequency in gigahertz I have put, and attenuation, you can see that there are different windows. We have H2O, water droplets. They affect the frequency bands from 20 to 30 gigahertz. Then we have O2, right? There again we have high attenuation. That is around 50 to 60 gigahertz. right? Then we have H2O. So different, these are the gases which are available, or water droplets, which induces a lot of attenuation, right? Now, this path, so there's a high path loss. So path loss can be mitigated by using high gain directional antenna. So what we can do in massive MIMO, we can generate antennas which is high gain and directional, both using high gain directional antenna. Just see this diagram where we have these multiple antennas, and what we can observe that we have main lobe and there are very less power in the side lobes. The side lobes have very less power. We can beam these antennas to the intended user. So whatever advantage, disadvantage we are getting in millimeter wave, where that is a lot of attenuation and absorption loss, that can be compensated by these high gain directional antennas in massive MIMO. So that's why millimeter wave massive MIMO is one of the important technology to implement this revolution path of 5G. Right? This is very important. Now, what is the vision about 5G? So in total, how this 5G is coming into, how we are perceiving this 5G by, these are the market players. Just I'm trying to emphasize you that how we are perceiving 5G by different enablers, right? These are the companies like Ericsson, Vision 5G, industrial research perspective. So research as well as industry, both I'm talking about. What industry says, Ericsson say that it is a network society, affordable and sustainable. For them, 5G is a network society, fine, that is all good, and it is affordable and sustainable. Qualcomm, for them, Qualcomm, what is the vision? Enabling novel services, because we are able to provide new services. Connecting industries and devices, because we are talking about Industry 4 and IoT. So connecting industries, devices, and finally improved user experience. So Qualcomm vision is this for 5G, right? Docomo 5G is a very big company in Japan. Everything connected wirelessly. For them, it is 5G is all about, it should be everything connected wirelessly. Nokia, HETnets, 5G means heterogeneous networks, fine, is acceptable. Augmented reality and tactile internet, right? 5GPP, that is European Union, what they see, software driven 5G. So 5G will be software driven, scalable and sustainable. 5G now is again a research community. So unified frame structure concept, right? Frames should be unified for all the types of services. Abundant synchronism. Abundant synchronism means that we are talking about massive machine type communication where synchronism is not possible. We are talking about asynchronous transmission and orthogonality. And we are talking about non-orthogonal waveforms where NOMA will come into picture. The last part, that abundant synchronism and orthogonality, and talk about non-orthogonal waveforms, that is NOMA, right? Now, last slide, I will discuss about NOMA for 5G. So non-orthogonal multiplexes is one of the key technology for fifth generation wireless network and beyond. Because why it is key technology? Because it is able to add more number of users. Spectral efficiency is more compared to OMA, right? So more number of users is being added in NOMA. That you have to mean that, and that too with more number of users with higher spectral efficiency, right? The basic concept behind NOMA is to serve more than one user in the same resource block. Already we have discussed in the same resource block, that is time slot, subcarrier, spreading code. So time slot is what we are using in TDMA, subcarrier what you are using in OFDM, and spreading code what we are using in CDMA. So the same resource you have to serve more users. Basically divided into two main categories, namely power domain NOMA and code domain NOMA. So there are two types of NOMA. So what we are doing in power domain NOMA? Power domain NOMA utilizes superposition coding at the transmitter and successive interference cancellation at the receiver. So what we are doing in power domain NOMA, that we are transmitting users at different power levels. So users are identified by different power levels. Power domain NOMA. Till now, we are identifying users by unique time slots, spreading code, or tonal subcarrier, right? But now we are identifying users by different power levels. So that other dimensions are free. Time dimension is free, frequency dimension is free, code dimension is free, right? Everything is free now. Time and frequency dimension is free. Now users are identified by different power levels. So you can transfer on all the time or all the frequency. But it will induce interference. Always keep in mind that whenever we are trying to violate that orthogonality criteria, there will be a lot of interference. So we need to have a successive interference cancellation at the receiver. And other part of NOMA is co-domain NOMA multiplexes the competing users in the code domain where a finite number of users are allowed to interfere with each other. In code domain NOMA, basically what we are doing, basically it is an extension of CDMA. We are trying to design low density codes, LDS codes. So LDS codes will have low cross correlation. Their interference will be less, and we are able to add more users. One example, already I have shown you that by designing this low cross correlation codes, by using channel overloading, the same concept as we use in 3G also or 4G also, where we have designed a set 2 codes, which are non-orthogonal to set 1 codes, but their cross correlation is less. But if you go on adding users, the interference will grow, and we need to have a interference cancellation receiver. Now, last slide, that is on cooperative NOMA. This is all about NOMA, now cooperative NOMA. So just you can see that we have a base station, and there are near user and far user. This is the concept in because some users are close to base station, or rather a far user, and we are using relays, and that relay will help to make the company. So these relays are also transmitting. These relays are also receiving signal from the base station. These users also receive signal from the base station, and from the relay we are having an alternate path. From the relay we are having an alternate path so that their service is more reliable. So cooperative NOMA networks can be classified in 2 categories. The first category relies on the dedicated relay cooperation, where dedicated relays are deployed to assist the communication between the source and NOMA users. Other is that the second category relies on the user cooperation, where the NOMA users having strong connections to the source serves as relays. So just see this. This is cooperative NOMA of second category, where this near user is a strong user. So it will also help the far user. It will act as a relay here. It will act as a relay and will serve the far user, right? So this way, what we are trying to cooperative NOMA is also where when we are adding so many users in 5G, there will be always some users which will be far from the cell. They will be at cell edge. They will be indoor. They will be in the basements, right? So their link will be always unreliable. To make them reliable, what we are doing, we are adding some extra relays, and the strong user also can be act as a relay, and they can support the weak user, that is far user. With the NOMA users having strong connections to the source, serve as relays to have the NOMA users having weak connection to the source. Right? This is all about cooperative NOMA, and we are what is happening in 5G, that network is becoming very complicated, right? We have different types of devices, we have different types of services. The requirement of different requirements of different services is very different. So if we use this general methods, they are not going to help us. So we have to rely on artificial intelligence, right? Machine learning concept, deep learning concepts, where we are trying to model this wireless communication networks or 5G networks in such a way that we can utilize the concept of artificial intelligence to add more services, to add more users on this complicated scenario where we have different type of devices, different types of services, massive devices, massive connectivity, right? To take all this, artificial intelligence is going to help us in NOMA as well as in the overall design of 5G. So what's the conclusion? While 5G will integrate the latest technology challenges to achieve the best possible performance, LTE Advanced is expected to evolve as part of 5G technology in a backward compatible manner. So LTE Advanced is, so you may ask that this 5G and beyond 5G we are talking about, whether this LTE or 4G will obsolete? No, not now. For the next 10 years, I think that LTE will be always there. And what we are trying to do is that we are trying to integrate the latest technology challenges to achieve the best possible performance. And this LTE advance is expected to evolve. So what we have to do, we have to use new technologies like SDN, two-dimensional MIMO, LAA, so that this can be part of 5G. So LTE advance or 4G will be a part of 5G for next 5 years, I can see, in a backward compatible manner. Evolution of LTE advance will continue in a backward compatible manner with the goal of improving system performance in bands of below 6 GHz. But this LTE advance to 5G will be around 6 GHz only. Beyond 6 GHz, we are not foreseeing. And the second track is commonly known as the new radio track in 3GPP, which is not limited to backward compatibility requirements and can integrate breakthrough technologies like millimeter wave, massive MIMO, right, to achieve the best possible performance. And that will become, 5G can become a reality. So what is expected that by 2022-23, we'll be able to have this enhanced mobile broadband services, the first category of services. And maybe by 2025, we can expect to have this ultra reliable and low latency communications, right? This is the way we are expecting 5G to evolve, right? These are a few references, and thank you.
Thank you very much, sir, for your nice session. And all participants are requested to ask their, if you have any query, you can ask from the speaker. Sir, I think we should conclude the session. Sir, all are requested to switch on your camera for a group photograph. All participants are requested, kindly switch on their cameras.
Thank you, sir.
Thank you, madam.
everyone.
Thank you.
Thank you, sir. Thank you, everyone. The next session will be at 1:30 p.m. Kindly join the session.
So, madam, mostly participants are your students or faculties from engineering colleges here?
So, faculty members from engineering college.
Okay. So they may get some research idea, right? Probably because
Definitely.
understanding 5G not so easy, right?
Exactly.
So maybe they get some research directions, they can work, and they can contact me. Even you can share my mail ID. They can contact me off the line also, right?
Definitely.
So that I can. Thank you, madam. Thank you.
Thank you, sir.